Hello, my name is Ronaldo Montrose, and I'm going to present M11. It basically says that if A is a subset of B and B is measurable, then the outer measure of A plus the inner measure of B minus A equals um, the measure of B. So I'm going to present that in two steps. This is the first step that I'm doing now. Um, So the next page, we have this diagram here. Just going to go over the legend, but because we're going to go back and forth to these slides whenever needed. So this piece here, wherever you see this vertical bar like this, is not vertical bar basically. So this means the intersection of B and G. If the bar are leaning like toward um, right, this is B minus G, and wherever that has this multiple dots, this is actually B minus A. So to prove that, we consider set G, such that A is a subset of G, as it is in here. A is inside G, and we show it two different ways, right? So A here, and this is G, so A is a subset of G. Um, from the Venn diagram, we see that the intersection of B and G is a subset of G itself, if we look at the Venn diagram, right? So this is the intersection of B and G. This space here, this is the intersection, right? It's a subset of G, and the same is true for this Venn diagram here. So because of that, we can apply property in page 31 um, of the Jones book, property 04. So since G is a superset of G intersection B, we can say the measure of B is greater than or equal than the measure of G enter B. Um, and from there, we can go ahead and add the inner measure of B minus A on both sides of this equation here. And so one thing we need to note here is that then B minus G is actually a subset of B minus A, given that A is a subset of G. So because of that, we can also apply property in page 43, right? It's property star 2 in page 43 of the Jones book. Everything we refer is in the Jones book, basically. So in that case, we'll be able to say that the inner measure of B minus A is actually greater than or equal to the inner measure of B minus G. So with that, we will be able to replace the inner measure of B minus A here. So let's go to the next slide. So we replace the inner measure of B minus A by the inner measure of B minus G. Uh, and from there, we said that instead of having the inner measure of B minus G, we just say is the measure of G. Why? It's simply because the Lebesgue measure of a set is the same as the inner measure of that set, given that the set itself is measurable. So in that case, we need to find out if B minus G is measurable, right? If B minus G is measurable, you should be able to apply this property instead of writing the inner measure of B minus G, we write just the Lebesgue measure of B minus G. So we said that B minus G is measurable because it was given from the problem that B is measurable from the problem description, right? So it says that that G itself is measurable, right? As you said here, and we know that we started by saying that we consider an open set G, so that A enter G. So we know that all open sets are measurable by property M7 in the Jones book. So and we also know that the complement of 2 measurable set is actually measurable by property M3. So that tells me that B minus G is actually measurable. Since it's measurable, we can apply that property. So we can say that the inner measure of B minus G is actually equals to the actual Lebesgue measure of B minus G. So we're able to replace that in here. On the next slide, so we'll replace it here. Instead of the inner measure, you just got the measure of B minus G. And since B minus G and B intersection G actually disjoint, so we will be able to apply property P2 and page 28. If these two sets of disjoint, we will be able to take the union instead of writing the B minus G plus the Lebesgue measure of B minus G and the Lebesgue measure of B enter G. So we just write them as a union of two sets, of these two sets, because they're actually their intersection is actually empty. And from there, in page 2 of John's book again, we know that B minus G is the same as B intersection G C G complement, right? So we just replace that in here. And we know that formula here, if we have three sets, A, B, C, A enter B union B enter C is actually equals A enter B union C. So in our case here, this is the same thing we have here. This is our, let's say this is our set A, this is our set B, right? And this is going to be our set C, referencing to this, right? So we're able to say that B intersect G union GC as per this property, set property, right? So, and from there we know that G union GC is actually the universal set, is the universe. So we replace it by that here. We get B intersection the universal set. That is because G union GC equals the universe. And then since B is actually a subset of the universe, so the intersection is B itself. So that's how we're able to prove this here equals the Lebesgue measure of B, but we still have a little bit left to show, because we have G here, and so we said that since G was an arbitrary open set where A is a subset of G, and we know by the definition of outer measure, right? So we're able to replace the measure of G, which is an open set. We know A is a subset of G. Then this is actually the outer measure of A, right? So this finished the first part of the proof. Now we're going to look at the second part, which is actually very short. So the second part will show that the same thing, right? But we'll start with a compact set, right? So we said that K is in a compact set if K is a subset of B minus A. So if K is a subset of B minus A, that automatically said that A itself is a subset of B minus K, right? So you can actually see that in the Venn diagram, right? So if we go in our Venn diagram that we have at the beginning in page 2 of our slides here, so if K is in a subset of our B minus A, A is everything where we have these dots here. This is the set of B minus A. If K is inside this, right? So basically A itself is going to be a subset of B minus K, because if this is B, right, and K is inside here, so A is automatically inside B minus K. So because of that, we are able, by property 2 in page 43 again, said that the outer measure of A is less than or equal than the outer measure of B minus K. And from there, we just add the measure of K on both sides, right? We can do that. And we know that all closed sets are actually measurable, again, by property M7. and we know that K is compact. All compact sets are actually closed and bounded. So K is closed, therefore it's measurable, right? And by property M3, in page 49 of the book, B minus K will also be measurable. Why? Because B is given to be measurable, and we just um, show that K is measurable by property M7. And so B minus K is actually measurable. Since B minus K is actually measurable, uh, we can say that um, the outer measure of B minus K is actually the measure of B minus K, right? So that is a property of Lebesgue measure. So we will be able now to replace the outer measure of B minus K here by just B minus K. And that's what we do here. We replace it by B minus K. And then, and this is by the way I explained it in the previous slide. And from there, these two sets are actually disjoint, right? So the intersection is empty. So we will be able to take the union of these two sets, B minus K and K. And we know that K is basically a subset of B, right? So how do we know that? It's simply because K is a subset of B minus A. If it's a subset of B minus A, that's automatically make it a subset of B. So because it's a subset of B, it's just the measure, right? So this here, B minus K union K is just B because it's a subset of it. So that's since K was arbitrary, and we said that lambda n is the outer measure of A plus the inner measure of B minus A. Because K was arbitrary, we can just place it here. Is just less than or equal than the measure of B. This finish my proof. Thank you.